I'm here to talk about Bitcoin security and how it's a kind of a house of cards, so that you should pay attention on what you're doing, otherwise it's going to fall. First of all, who am I? I am jaonoctus. I work at SegWit. It's a Lightning wallet, and I'm also a developer advocate at 21. And I've been studying Bitcoin for the past, I would say 11 years. And here are my contacts if you want to get in touch. I'm going to give you guys 5 examples of how Bitcoin could kind of break, or how you could mess up with your stuff. The first one was the SegWit upgrade. It happened because of this, a ECDSA malleability. And it happens like this. Let's say you have a route transaction, this beautiful hex here, and its transaction ID is computed by its contents. So that, let's say if I change 1 bit, the last one, let's flip it to 1. The XID changes, right? Because we're doing a double SHA-256 here, right? So yeah, it changes. But then the signature would be invalid, right? Because I changed the content, and on the signature formula, you were committing to a message, which is the transaction itself, right? So that if I change the message, the signature is not valid anymore. Let's go back to the first example. This part here, as I said, is the signature, right? But it's 2 pieces, actually. The first part is what we call a nonce. The second part is the signature. What if, instead of changing the content of the transaction, we change the signature? The transaction ID changed again, because I changed the whole message, like the whole transaction. But the signature is valid now. How the fuck? Basically, I'm going to break down the ECDSA signature formula here. We first take a nonce, and the little k here is the private nonce, which times the generator points of the curve, so that we have a point in the curve, which is the public nonce. And then we get the x coordinate of this point, and we're going to call it as little r. And then the signature is the nonce inverse modular of this value times your commitment plus the nonce, the x coordinate of it, times the private key, right? That's the ECDSA formula. The way we verify it is that we take the commitment times the inverse modular of the signature, and then the same operation, but with the nonce. And then we recompute the public nonce point by doing this operation here. And then we check if the point that we computed is the same, the x coordinate of it is the same of this little r here, which, let me go back real quick, which we say the value here. But the way I changed the signature in order that to be still valid is basically doing, I take n, which is the field, and then I subtract the signature. It's basically the same as saying my S prime is going to be minus my signature mod n. Same operation again of verifying it. I take my commitment times now my S prime, and then my nonce times S prime again. If I do the computation, I'm going to get minus R. But it doesn't matter to us because in the end we are going to do the mod n operation. So the minus here would turn to the same value, so that the signature is still valid. The way that the modular operation works, let just me simplify a bit here. Let's say I choose this value here, 4, as my signature. Then I'm doing mod 12 in this case, because it's a clock. I'm going to get the same value, it's 4 still. But if I get the minus 4 here, I'm going to call it as S prime. And then I'm going to do the mod operation it's basically saying, okay, I'm starting from this and then going back 4 positions. So we end up with another value, so that S prime is equals 8, and it's still a valid signature if we do the computation by verifying it. SegWit solve it by getting, actually by enforcing a rule here. Not only by not using the signature and removing it and placing it into what we call witness, but also signatures now, they must be, not sure if you guys heard about it, but it's a low S. What does it mean? Let's say we have this field here from 0 to n. We get the half of this value, which is n by 2 here. So that's half of this field. My signature, to be valid, it must be in this range here. If it's a 8 in this example, it will be sitting kind of here, and then it's invalid. But yeah, at the time, it was possible to do, like before SegWit in the legacy transactions. And they say that it was like one of the root causes of the Mt. Gox hack. I mean, at least one of them, I didn't verify it. Another example here is reusing nonces. Again, let's say you have 2 transactions. They are different. They are spanning from different TX IDs, and although they have the same value here. But if you pay attention, if we look into the signatures, they kinda similar, right? Yeah, because the first part, as I just told you, it's the nonce. So they have the exact same nonce. And that's an issue. Let's see why. I'm going to demonstrate with Schnorr signatures now, but it happens in any of either Schnorr or SDSA. Let's say we have a nonce times the generator point, so we got the public nonce, and then you do a commitment, which is a hash of the x coordinate of this nonce, your public key and your message, and then you do the signature by adding to the private nonce the commitment times your private key, right? That's the formula of Schnorr signatures. If I take two different signatures now, S1 and S2, but they are using the same little k here, which again is my nonce, so I'm reusing the nonce. If I subtract signatures S1 minus S2, I get this, right? And then if I rearrange the terms here, you guys can see that I'm doing my nonce minus the same value, which is 0, so it cancels. And I'm left with one signature minus the other equals my commitments being subtracted times my private key. Again, I can rearrange this so that I'm left with a private key. If I do one signature minus the other and then multiplies it by the inverse modular of the commitments, I can recompute the private key. The library that we use, libsecp or any other that is well implemented, they would use a deterministic nonce so that we don't have this issue. Another flaw that we have is in the BIP32, and everyone here is using it, because if you have a wallet with your 12 or 24 words mnemonic, you're deriving with BIP32 in the end of the day. And there's a way that, I mean, you're dealing with private information, right? You have your xpriv or you have your mnemonic, but let's say I was able to get your xpub because you gave it to me. I was paying you for a service or something so that I could pay you every time on a different address. That's why you gave me your xpub for this wallet. But let's say for some reason or in some way, I got one of your private keys, right? Just one, just for your, let's say, first address of that wallet. So I got your xpub and your private key. GG's. Why? Because I can recompute every single private key of your wallet just by having your xpub and one of your private keys. That happens because the way BIP32 works is that I do this computation here. It's a HMAC SHA-2 512, and then the information that we use here is your xpub, and then every single private key that is generated for every address that you have on that wallet is this. Your private key is the result of these 64 bytes, but we got only the left side of it. So that's why we see here IL, it's the left part, plus the key par, which is the private information, so that any private key that you have is this minus this information. But I have everything here, so I can recompute any other that you have. When you see the derivation path, let's say SegWit is 84 and prime, that prime there, like that line, means that you're using on this computation your xpriv instead of your xpub. So that even if I have that two information, I cannot redo this math because I don't have your xpriv here. Another interesting topic is sidechain attacks, and I could be here talking all day of like every single possible way to do it. There's many. One example is dark skippy. It works by leaking your private key in the signature. We just saw it, but it's another clever way to do it. Again, a transaction, a signature, the first part here, it's the nonce, right? It seems random to us as human beings, like we just see a fucking huge number and it's in hexadecimal. So yeah, I don't even know what numbers it is. It looks random to me. But what if the hardware wallet that you're using, if you don't flash it by yourself, you didn't like check the code on what it's doing, it could be leaking your private key in the nonce. Like the last, let's say the last few bits is one part of your private key. And if you are a target, I would be watching your transactions, collecting the nonces, like the last parts, and then I would be able to, at some point, get your xpriv, your mnemonic, whatever I'm leaking via the nonces here. The fifth one, the last example I want to give, is low entropy seeds. Again, if you are generating in your secrets in a good way, you have 2 powered by 256 possibilities. It's basically the fucking entire universe. And you have to select the same atom as I'm selecting it. But then, if you are using low entropy seeds, it's basically reducing the field, the target. So that, imagine that instead of generating a fucking huge number, we were rolling a dice from 1 to 6. Like my sister could guess it in 6 seconds if she could talk 1 per second, you know? So that you should use a good source of entropy. And then I just wanted to finish by saying that Bitcoin security, I mean, Bitcoin is not secure because it cannot break. It's secure because we can know what would break, so that we avoid using bad patterns or bad implementations. That's it.
Questions?
Any questions?
Wait. So when you were explaining about the modulo thing and you draw that scale from 0 to something and something in the middle, you said that we should choose the lowest. Do you remember that? Why choose the lowest? Why? I don't know. That's a dumb question because I don't know if the other side is possible. Why not the highest? Is there any reason for it, or just need something?
Yeah, it was defined when we were upgrading to SegWit. Let me see if it's still here.
Yes, exactly.
Right.
Why not the red part?
Because otherwise, if you are on the high S or the high values here, if you do the operation, you would get on the other side. by doing the computation. So it's going to like back and forth.
Okay.
So that we just avoid this thing that happens if you are on one part, you have another possible way, another possible value. You're basically cutting the possibilities to only one possible value.
Okay. I got another dumb question. Can you go back to the slides where you showed the TXID changing?
Yeah.
Yeah, any one of these. You say it's right. You're saying that's a double SHA-256, right? A TXID. Right. Why it needs to be a double SHA? Why not one round SHA-256? Do you know the reason?
I mean, there is. It was defined by Satoshi.
Yeah, because Satoshi
didn't need it to be exactly. I know that there is some attacks that could happen by pre-computing a value or a part of the hash, so that if you do it twice, it wouldn't happen.
Okay.
I don't remember the term of this attack from my mind, but yeah.
Okay, thank you.
Next question. Don't be shy. There you go. Thank you, Pedro.
Just to make sure if I understand what you said, on some applications you have the part of the private key leaked on a transaction. Is it right, or did I miss this part?
There is one possible attack of a bad implemented wallet, let's say, that could leak your private key through the nonces. Let me get to that slide here. Yeah. It's not every wallet, but you could like add information into the nonce so that you're leaking your private key through time.
Thank you. Just to make sure.
Yeah, and again, well-implemented wallets would generate your nonce in a deterministic way so that you can validate if it's actually not a random, but what it should be, instead of having secret information in its number.
Okay, thank you very much.
Thank you.